people involved.
All right, we're live now.
Okay, welcome everybody to another virtual PQI session. Our first speaker today is Andrew Daly, a PQI dues-paying member, and I guess the eastern outpost of the PQI family. Andrew's a professor at the University of Strathclyde and recipient of a number of awards and honors. And take it away, Andrew.
Great. Well, thank you very much, Michael. I'll just set up my screen sharing, and meanwhile, say it's a great pleasure to be here for this this PQI session. And thank you very much to all of the people involved in setting up these things and making sure that even if it's spread out over a few months, that we got our PQI event again this year. So great, as always, to be associated and to be the, as Michael said, Eastern Outpost here in Scotland. And of course, my title slide has the picture of typical Scottish weather here over Loch Lomond. So of course, the session today is on quantum optics, and so what I'm going to talk about from a theorist point of view is some of these really interesting and fun systems that experimentalists play with in our field, and of course we've got two examples of people who've done a lot with these sorts of systems coming in the next two talks from Dan and from Tom. What we normally sort of look at are these systems where we take an AMO system, very often with cold atoms, but a lot of the things I'm going to say apply equally to trapped ions or to polar molecules. So here, sort of from the example, sort of atoms maybe in optical potentials, sort of systems maybe of trapped ions, long chains of trapped ions, systems of neutral atoms in tweezer arrays where you can excite them to Rydberg levels, atoms in optical cavities, or indeed trapped polar molecules. And what you can do in this field is, these are AMO systems where we understand the single particle physics and also the interactions between particles very well. And so from first principles, we can write down the microscopic descriptions of these systems, and we can go and engineer in the lab things like Hubbard models or spin models. And the emphasis I really want to make here, especially from a point of view of why this is particularly interesting as a theorist for a potentially broad audience, is that we really have the ability to understand from first principles where these models come from and what approximations we're making when we write them down. We understand not only that we get the Hubbard model, where we describe atoms tunneling between neighboring sites and interacting when you get two or more on one lattice site, but we can also write down microscopic descriptions for dissipation in this system. So if you want to know where the decoherence and the noise comes from, we can write down microscopic descriptions for that as well. And then typically, because the energy scales you have in the system, these systems are much smaller than the energy scales that you have, for example, in the solid state. You have time scales that are much longer, and so in these systems, as I'm sure you'll see in some of the things that Dan and Tom are going to show you, AMO systems in general, you have the ability to make measurements time dependently of these systems, really track sort of dynamics in the system in real time from some starting initial state. So the broad sort of perspective as a theorist is that these are then interesting for very many things, and it's fun to look at many body physics that you can implement in the lab in these systems and ask, where can this take us sort of over the coming years. We've been thinking a lot about sort of things like many body physics and potential connections of the physics we can study with cold atom quantum simulators to the sorts of things that people look at in the lab in solid state physics. For example, maybe some of these transport systems that Jeremy, for example, has in his lab in Pittsburgh. We also are very interested in understanding how the control that we develop over these systems, when we start thinking about them as controllable many-body systems, can be used in interesting ways to enhance other applications of cold atoms, particularly to things like atomic clocks and other devices for metrology and sensing. So we're mentioning just before the start of this, in the quantum science seminar this afternoon, a really interesting talk from Anna Maria Ray, who's collaborating Gilla with also with Jun Yi. And Anna Maria was telling us about different ideas in using many-body physics with cold atoms that could eventually be used maybe to enhance things like optical clocks, specifically in some of these best sort of optical clock experiments that they have at Gilla. And eventually what we'd like to think about in this field is sort of programmable simulation that really maybe goes beyond just looking at fundamental physics. We maybe want to be able to study models that we're interested in from material science and start to maybe ask if we can use these sorts of AMO systems as programmable quantum simulators that will help us to solve problems that we can't easily compute on a classical computer. We might have a model for a material system we'd like to solve, but it's a large many-body quantum problem, so it's hard to maybe solve for the dynamics of that. Classically, we'd love to be able to program these sorts of models into these AMO systems, solve them there, and get information that can help us understand new aspects of materials design. Maybe, in the sense of thinking about these devices almost like as wind tunnels for quantum dynamics, or if you like, as analog computers to solve these problems. So of course, one of the big questions is, when you start dealing with these systems in the lab, how well calibrated are they? Where are the imperfections? To what extent can we really think about them as reliable calculators for these types of questions? So as a theorist, something that we've been thinking about in the last little while is trying to, in a detailed way, study where we think we really get a practical quantum advantage for studying quantum dynamics here. Where can we really say that we reliably beat what we can do with classical calculations? So for that, when we think about analog quantum simulators, and we'll take, for example, cold atoms and optical lattices, where microscopically from first principles for atoms in the lowest band of an optical lattice, you can think about particles tunneling between neighboring sites and interacting when you have them on the same site. Here we really get microscopically from first principles a Hubbard model, and we also know what approximations we've made. So we know on what level we have other terms that are there that we maybe didn't want in the Hamiltonian. We also know how to characterize noise. We also know how to characterize decoherence in these systems. So what we're asking is, can we go and characterize the level of error that we expect to get when we go to try to compute, if you like, time-dependent dynamics in these experiments, and try to understand where really we can say that the error that we expect out of this is bounded below the errors that we get from the best available classical simulations. So, of course, when you start making these comparisons, you have many choices that you can make. And what we do is we take the choices where we have the best defined answers for where are the limits of classical simulation. And for that, it's really taking Quench dynamics from some generic initial state evolving under a Hamiltonian, because we know how to characterize where, for generic problems, classical simulations, as we have them at the state of the art, really start to break down. We then look to quantify the errors that we would like to be able to restrict to in measurable observables that we'd like to get out of the experiments. And then we go to account for calibration errors in the experiments, these unwanted Hamiltonian terms, errors in initial state preparation, and then also noise and decoherence. And because for these sort of quantum optical systems, we have an understanding of where all of these things come from microscopically, it's possible to write down the extended models that include these and start to estimate what it does to have these imperfections to the sorts of correlation functions you might want to get out in the dynamics of these quantum systems. So in this particular case, taking this example, what we did is we went through, and of course the first question that you'd like to ask, why do we choose Quench dynamics, and what are the errors that develop in sort of state-of-the-art classical simulations? And the state-of-the-art classical simulations for dynamics, for generic quantum dynamics in these systems, are calculations based on tensor networks or time-dependent DMRG and related calculations. And if you want to do exact calculations for quench dynamics, what we generally find in these systems is that it becomes exponentially difficult to keep simulating these sorts of quantum systems to longer and longer times as they start to thermalize. There's been a lot of work done to understand this sort of over the years. It involves essentially the growth of entanglement entropy across the system that when you write down matrix product states leads to eventually an accumulation of errors once you can't anymore represent the level of entanglement that you expect to get in the experiment. And what you see is that if you can evolve accurately to a particular point in time with a particular size of the matrices that you're using on a classical computer, then in order to go further in time by a linear increment, you need to go to exponentially larger matrix sizes in order to accurately capture those dynamics. And if you don't do that, then in most generic situations, although there are ways to extend by factors of 2 and there are many tricks to maximize how far you go, eventually you always kind of hit this wall where then the errors in any correlation function you're trying to calculate grow very, very rapidly and saturate to values where they become unuseful, sort of tens of % of errors in quantities of the order of 1. So then you can ask, well, okay, that's fine. We understand that there's a limit to what we can do in terms of calculating a many-body quantum system classically. How do we make sure that we can restrict the errors coming in the experiments only to a few %? So this is where you can go and you can ask what the hardware requirements are to really get an advantage then out of these analog systems for realistic timescales. And so by doing sort of calculations, taking into account the various imperfections I mentioned before, we identified that in current experiments we expect that the major cause of errors in the final correlation functions are calibration errors in the parameters of the experiment, and that over time, so we can simulate this classically, this tends to lead to errors that even for sort of 1% calibration errors are of the order of much less than 1% in the sorts of correlation functions you want to measure. And where we would estimate the sort of state of the art is in experiments with cold atoms and optical lattices, it's about halfway between these lines. You're really looking at things that are well below the sort of 0.1% level in terms of what we would expect for errors in the typical correlation functions that we would like to measure. Other errors due to imperfections we expect to contribute less in these sorts of correlations. We also looked at decoherence that we can model in these systems from first principles. We also looked at laser noise on the potentials. And what we found was that decoherence in particular is the thing that will eventually limit the evolution in time of these systems, basically because eventually it decoheres this to the level that you're again not representing the dynamics that you would like to represent. But again, this is something that we can in these AMO systems derive from first principles and model, see how errors are growing, how they compound in time in the system, and essentially how we can make sure that we know at what level these errors are in particular correlation functions. And again, for typical levels, in this case of spontaneous emission, which in current experiments are actually at the smallest levels that we indicate here, because the lattices tend to be very far tuned, again, the errors that we get tend to be very small. But you get an idea when you see the larger rates that we've simulated here, how the effects of decoherence do tend to compound in time. So that will ultimately be at the moment the limiting factor for how far we can push these things in time. When we ask how far we can really go, one thing that it is quite clear that conservatively from these estimates that we can extrapolate these things also to small 2D systems, which we do via adding rungs to a ladder. In our dynamical calculations, we start off with in 1D. And we can understand that it's very realistic that you can evolve to times of the order of 10, or probably even more than that, tens of tunneling times on 2D lattice systems, which at the moment in the lab are anywhere from 10 by 10 up to sort of reaching 30 by 30 or so. And when you take these sorts of systems, then we understand that the errors should be bounded to a level of less than 1%, and we understand that they are much smaller than the errors we'd get for evolving over the same timescales in classical simulators. That means that in this sense, for these types of dynamics problems, that we really already have, in the sense, a practical quantum advantage in existing analog quantum simulators. We've made further comparisons also with the question of if you didn't want to do the calculations on a classical computer, but rather if you had a quantum computer and you wanted to do digital quantum simulation, what would the hardware requirements be on a digital quantum simulator to do these same these same sorts of calculations? I should say before I even show results that this is maybe an unfair comparison, because in the end the problem that you're trying to solve is native to the analog quantum simulator, and you can only solve the problems that are native there. Whereas if you have a digital quantum simulator, it's the ideal case, because you can then go ahead and program any Hamiltonian you like and solve any Hamiltonian that you like. So you have this flexibility that you don't have with the analog systems. The limitation, of course, that you're going to expect is that you're going to need relatively large size quantum computers to do these calculations accurately. And for the sake of time, I'll go through this quickly, but what we've done is we've estimated if we have a trotted decomposition error as the only error in the system, so if we assume a fault-tolerant digital quantum computer, then to do these same calculations for, say, a 10 by 10 lattice in 2D, we understand that you would need of the order of 1 million fault-tolerant gates in order to get the same level of error that we're getting out of the calibration on current analog quantum simulators for the same problem. I should emphasize that because we look at correlation functions for this comparison, and because we have some tricks in how we do the gates, we are actually at the point where these sorts of estimates are a few orders of magnitude smaller in terms of required gates than most previous estimates. But still, it's a little way off before we'll have hardware that really allows you to do these things in this form on digital machines. So the summary is it's fun as a theorist for these AMO systems, because you can really model all of the imperfections from first principles and try to extrapolate out to understand where we get an advantage from using an analog system. And current analog systems of the sort that you're going to see in Dan's talk are already in a position where we believe that you can do things that are genuinely beyond what you can calculate on a classical computer in a reliable form. The digital side of things is coming, but of course important for generic problems. These systems are then interesting for very many things, and we've been thinking in a lot of directions I don't have time to tell you about, including topology, using dissipation to do fun physics, understanding quantum transport out of these things, and various applications. So with that, I'll show you the most recent group photo from my group at the University of Strathclyde. Thank them. Thanks Stuart Flanagan from my group, who did the calculations on analog systems. Thank Natalie Pearson and Matthias Troyer, our external collaborators who did the gate estimates on the digital side. And I'm looking forward to any questions you have. So thank you all.
Yeah, the usual silent clapping of the Zoom. Okay, so I don't see the YouTube chat, Jennifer.
No questions yet.
So then I guess my question for you, Andrew, is like this: the thing that really jumps out at you is, how bad quantum computers are at this thing. Mm-hmm. And I guess that's because sort of computation is not usually having all your bits talk to all your other bits at the same time, or I mean, does it tell us something about the difference between computing tasks and sort of simulating a system?
So I think that I mean, if you go back really to this sort of comparison that I've got here, I think that the point is the following: we're asking the quantum computer to do something that's genuinely hard because we've got a many-body physics problem where if you really look at the dynamics, it's a closed system and you build up a lot of entanglement. So this is a naturally hard test for a classical or a quantum computer. The quantum computer is, and so therefore the requirement is that you really have good fault-tolerant quantum hardware. It's the normal story for quantum algorithms where you expect a really substantial quantum advantage. You're normally going to need a big quantum computer, and it's exciting if we can get there because there are all manner of material science problems that are relevant for industry, catalysis problems for chemistry, and that could be solved this way. So this would be very exciting, and of course that's why people like you, Michael, are investing so much time in the lab. One of the many reasons why you're investing time in building, up the capabilities in digital hardware. I guess what I'm saying is that for these specific problems that you can implement on an analog device where it simply has home ground advantage, if you can calibrate it and control it really well, then it can actually already demonstrate these calculations with a practical quantum advantage, just for those models that are native to its own dynamics. And what I'm saying here is that decades of quantum optics have got us to the point of really good calibration of these systems.
Okay, great.
Follow-up question. So Andrew, I mean, aren't you in some sense underselling this? Because you're saying, oh, this quantum system that we've engineered can only do, can only be simulate its own behavior, but you've programmed, or the experimentalist or whatever programmed that behavior, and you can change it. You can move within a parameter space and look at a wide range of systems. So it seems like it's more general than just, oh, it can only do it, simulate its own behavior.
It's very true. I mean, what these things do is they give you access to a class of problems, and that class of problems is going to be interesting, I think, in the coming decade for doing lots of really interesting things in many-body dynamics. And people are demonstrating that in the lab all the time. And I guess what we're saying on the theory side is that we really believe that this is reliable and going beyond what we're doing in any sort of classical simulations. I guess what I'm saying is that once you get to really complex problems of the sort that you get in chemistry of solids and so on, you may find that the models become too complicated to really implement them directly with cold atoms and optical lattices. And at that point, or other similar sorts of systems, and at that point, you will eventually find a way to win for doing a vast array of chemistry and material science problems if you could build a fault-tolerant digital quantum simulator. But for the next 10 years, we're already in a position where we can have fun with a device that has a practical quantum advantage for lots of problems that are useful for science. And yes, there's a whole parameter space out there that one can go and explore.
Okay, great. So to stay on time, I think we have to move on to the next speaker. If Andrew, would you be so kind as to take down your thing, and Dan, if you'd like to start loading yourself in. So our next speaker is Dan Stamper-Kurn, who is a professor from the University of California at Berkeley. He also has an array of prizes and honors, but you probably saw him in the news this week for being the director of the new, one of the, I think, 3 new NSF Quantum Leap Challenge Institutes that's going to be centered at UC Berkeley. So take it away, Dan.
Go back to this and give myself a pointer. Aha, good. All right. Well, I must say it's very disappointing to be with you all via Zoom. I was very much looking forward to the in-person PQI meeting, and I was really grateful for the invitation to come out in April when it was unfortunately made impossible, because I was really looking forward to the chance to come by to see a lot of good friends that I have in Pittsburgh, and also really to get to know better the really wonderful scientific environment that you guys have built up there. So it's really quite impressive, and I would have enjoyed the visit. So hopefully we will flush this from our system, and I'll have a chance to pay a personal visit when things clear up. So with that, let me tell you about some of the work that's been going on in my group, in particular in the area of quantum optics. And by way of a broad introduction, I'm going to tell you about a set of experiments where we take a quantum system that happens to be a gas of atoms that are cooled to very low temperature. We place them inside of an optical cavity where they interact with a single mode of light that is near an atomic resonance. So there's a strong polarizability and a strong response of the quantum system on the light. And we drive that cavity, we look at the emission from that cavity, and we make conclusions. And generally, this system I regard as a platform for studying quantum systems in general, but maybe specifically, given the vast amount of interest in quantum science and technology at present, I want to say a few words about how this addresses one of the central questions in that recent focus, which is really understanding better what quantum systems in general are capable of. We have talked about quantum computing as one application, and then I guess how to make use of them. So the system that has been built up in my lab and other labs elsewhere as well can address this question in a variety of ways. One area is to think about the concept of quantum sensors that make use of quantum coherence and also quantum entanglement to make more refined measurements and potentially to make discoveries. So kinds of questions that we've been asking in our physical system is what's sort of the minimum signal that can be detected by such a sensor, where you want to study the quantum system by the influence that it has on a cavity field. That cavity field leaks out to your detector, and via that you make inferences about the quantum system. And then secondly, given that we have such quantum sensors, what kind of new science can we uncover? And I'll talk about some of our thoughts in that regard more recently. A second question we can start addressing in the system is to understand quantum matter that is not, let's say, quiescent and living in some static Hamiltonian, in some energy conserving space, but really a driven and an active form of quantum matter. And in this case, we can think about a quantum system that is behaving in response to a drive by the interaction with this dynamic cavity field. And we can start asking new questions about this kind of non-equilibrium quantum matter. And one of the more interesting ones from my perspective is understanding whether there's any universal behavior in non-equilibrium quantum systems similar to what we're familiar with in quantum systems that are at equilibrium. So I'll touch upon that a little bit during my talk. And a third broad question that I've been interested in asking with this system is understanding what quantum systems do when they're subject to feedback. So for classical systems, this is a natural thing to do. After all, just about every functional device that we have in our modern life is stabilized by use of active feedback. So we might think that as we are starting to create quantum systems that are practical devices, we will want to apply feedback to make them capable as well. And there's a couple of ways in which feedback can be realized in our system. One is what I would regard as autonomous feedback, where just the construction of the quantum system itself, the way it's driven and the way it sheds information to the outside, naturally provides some sort of feedback stabilization towards some final state or some set of final states. Or alternately, we can think about some kind of active measurement-based feedback scheme, where we take information that is gathered about our quantum system and we change how it's driven in order to stabilize it and drive it to a particular target state. And the big question that we can ask there is whether we can indeed make quantum systems in general more robust, not just, let's say, quantum computers by something like error correction, but even maybe the quantum simulators that Andrew was speaking about, whether there's a way to stabilize those and get over some of the imperfections that he was trying to carry. Okay, so with the time that I have, I think I'll talk about two topics if time permits. One is sort of recent measurements we've been doing where we focus on using the cavity to measure the number of atoms in a fixed volume of space. And I'll tell you where that is leading us at present. I think it'll be sort of an open talk because we're still, formulating our ideas there. So I would appreciate your feedback and your questions. And then a second one is looking at how light interacts with certainly a quantum property of the atoms that we have trapped inside of a cavity, which is their spin. And I'll tell you some of the work we've been doing on observing and also conditioning spin dynamics through feedback. First, I should tell you about the physical system that we are using, and it's appropriate to have Tom on in the audience because this is Tom's baby. Well, is one of his early babies. He has more recent ones. And okay, so this is an apparatus where we take an ultra cold atomic gas and we place it in the space between two highly polished optical mirrors. The picture I'm showing you here is of an atom chip that Tom built while he was a graduate student at Berkeley. And you can see the wires in this atom chip as dark lines in this see-through infrared image. And these wires, these are electromagnets that are inside of a silicon wafer. They're used to grab atoms out of vapor and cool them using also laser light to low temperature. And then to translate them physically a couple of inches to locations such as shown by these sort of tombstone regions where we've, Tom has dug a hole through the chip. And with that hole, he was able to place two highly polished mirrors that are facing each other vertically. And they allow a resonant mode of light to be sustained, bouncing back and forth between those two mirrors, passing through this little hole. So what this chip allows us to do now is take a gas of rubidium, place it at any location we want vertically within this cavity, trap the atoms then in the cavity using some optical fields, and then use light that resonates in this cavity and is near the atomic resonance in order to interrogate the atoms on the inside. And so this is kind of a zoomed in picture of our apparatus. If you zoom out, you see Tom still standing there. Well, we wish he was still standing there, but he's got more important things to do. But the apparatus that he built with us in my group here at Berkeley a number of years ago has been just the most robust experiment ever built in my group and has been enormously productive scientifically. So I'm very grateful for all his contributions. Okay, so with this apparatus, we can take a gas of atoms, a gas of rubidium atoms, and trap them very tightly at a specific location inside of an optical cavity. And then we send a light into that optical cavity. It bounces back and forth, and it overlaps at the location where it has its maximum intensity. It overlaps with this gas of several thousand atoms. These atoms, I should point out, are rubidium atoms. And if the cavity light is close enough to the atomic transition frequency, then the phase of the light that passes through the atoms is slightly shifted by dispersive effects. And in the end, the net effect is that having placed a lot of atoms inside of the cavity, the overall frequency of the cavity resonance gets shifted by an amount that is, in this case, proportional to the number of atoms inside of the cavity. What that means is that if we interrogate the cavity and measure its resonance frequency, then we have a very sensitive measurement of the number of atoms that are trapped inside of this trap. And I'm going to make use of just that atom counting capability for the results in the next number of slides. So here's an example of our measuring that atom number dynamically as a function of time while something happens to the gas that's trapped inside of the cavity. And this was sort of our first attempt at doing this. It's kind of a crude measurement, but here's the idea. We take a gas of atoms that are trapped somewhere inside of the cavity. This is the overall trapping potential, which is a combination of an optical trap, but also a net force that is applied by a magnetic field gradient, which allows the hotter atoms inside of this trap to escape the trap and leave the cavity altogether. So initially, the cavity resonance has been shifted to the left in this graph by an amount that is proportional to the number of atoms. And if we probe the cavity, let's say at this frequency, we will see that the intensity of light that emerges from the cavity onto my detector is some low value. And now, as time goes on, atoms leave the trap because of evaporation, because these hot atoms escape the cavity. And so the number of atoms inside of the gas will drop as a function of time. And because of that, the cavity frequency changes as a function of time. And if we monitor constantly the intensity of light coming out of the cavity, then we see this variation of the intensity as a function of time. And we can then interpret this as a measurement of the number of atoms as a function of time during this experiment. Okay, so this was our starting scheme for making this kind of measurement. We've since become somewhat better at it. So what we do is we send light into the cavity. We measure the intensity of light going through the cavity using a receiver. And then we adjust the frequency of light going into the cavity so as to keep that intensity constant. So we're always measuring the atom number with very high sensitivity as the atom number, as the cavity resonance is sliding, let's say, to the right, and the atom number is dropping. So if I read off the frequency that is shifting this laser beam, I get a direct measurement of the number of atoms in the cavity as a function of time. Okay, I won't talk about this part too much, but obviously we have to take that signal and we have to think about what's the optimal amount of time to average that measurement so that it gives us a very highly sensitive measurement of the atom number, but doesn't obscure the dynamics that might be going on. Okay, so here's a number of single shot traces that are taken using this measurement. Okay, so here's atom number as a function of time while the atoms are being evaporated in single runs of the experiment out of the optical trap that confines them. These different measurements are performed with different intensities of light, so different probing strengths. And here is the average number of photons inside of the cavity. For these data, it ranges between 2 and about 10. So this is a pretty low light intensity measurement, right? So with n bar of 1, with on average, 1 photon in the cavity corresponds to just a roughly 3 picowatt beam of light that is measuring the number of atoms in the cavity. But nevertheless, we get a very good measurement of the atom number with low noise because we're using a very high finesse cavity where the light bounces back and forth many times and can interact strongly with the atoms. And from such a continuous measurement of atom number in a single run of the experiment, we now have the opportunity, I think finally in a cold atom system, to be making the kind of correlation measurements, but now in time, that Andrew was speaking of. So now we can examine a quantum system, or in our case, this cold atomic gas, and look at its 2-time correlation function or many-time correlation function by looking at the repeated value of measurements at different points in this time trace. In fact, these are single runs of the experiment. We can, because Tom has built us such a wonderful machine, we can repeat the experiments under identical conditions hundreds of times. And now we have many individual traces. Each one of these colored lines is an individual run of the experiment, whereas this dark line is the average value, and we average many of them. So we start seeing that there's the ability to make correlation function measurements. So for example, what's shown up here in these graphs is a comparison of the atom number at an early time, in this case it's at time 0, with the atom number measured at a later time, either an early time or a late time in the dynamics that we observe. So let's look at this graph. You see that the late time, the later time atom number is very strongly correlated with the early time atom number because very little time has elapsed between the first measurement and the second measurement. Whereas if I look at a much later time, let's say here at almost 300 milliseconds, then there's less correlation, right? So somehow the late time value of the atom number is not as strongly correlated with the early time value for lots of obvious reasons, because there's things that have introduced fluctuations, and also just because the atom number is smaller, there's sort of more relative measurement noise on it, and that ruins some of the correlations. Okay, so with these kinds of data, we can start asking a bunch of questions. And the question we've been asking ourselves recently is, what is the sort of
I'm sorry, I
thermodynamics?
just have a quick question.
Yeah.
Sorry, about the previous slide.
Yes, please.
So I'm looking at the long time correlation for the different numbers of photons, and maybe it's my, looking into this, but it seems as though the long time correlation is better preserved for the low photon density than for the high photon density, like 1.9 versus 9.7. 9.7 it looks completely uncorrelated, but there do seem to be correlations when n is smaller. Is that real?
Yeah, one way in which you know that's, so one of the things is larger photon number causes more heating, which ejects more atoms from the cavity. So you see, let's say here at n equals 10, the higher power measurement, you see that the atom number at late time is already pretty small. And the measurement noise on top of that small value is kind of a large fraction. The measurement noise, of course, isn't correlated. So you see then less correlation for these for these data than for these data. Even though the measurement noise is lower, so you think there should be stronger correlations with the actual physical quantities. In fact, because we've introduced a lot more heating, which is also a stochastic process, and also gotten rid of a lot more atoms, we've lost more.
So if
you're right.
So if you picked the N2 time to be one at a fixed N, but lower than the initial time, would those correlations be there, or is it just because of the lower number of atoms in it?
It's a combination. I'll get to some. Let me get to some of the details, and those are great questions. Yeah. So thank you, because we're trying to understand these data. We have just all these data. We're trying to understand what to make of.
Yeah.
Okay. So we need a framework in which to start understanding these data, and the framework that I'm suggesting is that what we're doing is studying some sort of thermodynamic process. Okay. So we're studying evaporative cooling here. We have a gas of atoms in some kind of potential landscape. And they live in some volume, but as a function of time, a bunch of atoms, because of collisions that produce some atoms at a high energy, a bunch of these atoms escape. If they emerge from a collision above some energy threshold, then they leave the trap. Okay, so there have been several treatments of evaporative cooling that try to describe, let's say, the rate, but also the fluctuations that are introduced through evaporative cooling. In considering, let's say, the density, the collision rate, the distribution function of atoms in the trap. And now in our experiment, we're able to make a very detailed examination of the ideas that are in these papers and maybe carry them a little bit further. So there's a lot you might ask if you had a thermodynamic treatment of evaporative cooling, but I'm going to ask just one specific question with our data. We're going to try to examine whether evaporative cooling is a linear, a superlinear, or a sublinear process. I think that would be the terminology, but this is what I mean by it. So first of all, let's just pay attention to the average value of things that is predicted by this thermodynamic theory. So consider that we have a gas that's undergoing evaporation from some early time T1 to some late time T2. There would be some theory that tells us that the expected number of atoms that I have at that late time, N2, is some function of the number of atoms that I have at the early time, N1. And that function is some function G. Okay. I'm going to, again, examine data at these two specific times, T1 and T2. And given that, let me define sort of two quantities. One of them is simply the ratio of these numbers, which tells me, on average, what's the fraction of atoms that's left in the gas. And the second is a similar quantity, but it's actually a derivative. If I vary the number of atoms in the initial sample, how much does the number of atoms remaining change with that? Okay. And in comparing these two quantities, P and A, I now have a way of telling you what I mean by linear, superlinear, and sublinear process. So in a linear process, I would expect that a change in the initial number by, let's say, 5% gives me a change in the final number by, let's say, 5%. Okay, and in that case, this quantity A would be the same as the quantity P, and that would quantify a linear process. So if I look at the difference between these two quantities, it would be 0. I can also have what I would say are superlinear processes. So that would mean that if I change the initial number by a small amount, I change the final number by a large amount. So if I have, let's say, 1% more atoms to start with, maybe that causes 5% more atoms at the end. In that case, this quantity A would be larger than the remaining fraction, and this difference would be greater than 0. I can look for that. Or I can have a sublinear process, one that tends to actually suppress variations as the process goes on. So even if the initial atom number is very different, maybe at late times, the number of atoms that we end up with is almost identical. So that would be a sublinear process. And I can, I certainly have this fraction in my data. And I also have this quantity in my data because the initial number that I measure in my experiment has some variation. And the final number I measure in my experiment has some variation. I can just see how they're correlated. Okay, so looking at these data, so specifically with n bar of 3.2 photons in the cavity, we're going to examine that quantity A minus P, which is a measurement of this super and sub linearity. And I'm showing data for different values of the remaining fraction of atoms in the gas and examined for different starting times. So either I take the data at very early times, let's say 10 milliseconds, as my initial number, and then look at all the data that follow. Or I look at data that come later on, let's say at 180 milliseconds, and I look at all the data that follow. And what you see is two very different characteristics in our data. If we look at the process as it involves the initial atom number, let's say at very early starting times, we have a process that appears very strongly superlinear. So small variations in the initial atom number lead to very large variations in the final atom number. On the other hand, if I look at data starting from a later time in the evaporative sequence, I see evidence actually of a sublinear process. So this is how we understand the physics at present. We think that what's going on, and this is just sort of an artifact of our experiment, is that at very early times, the fluctuations in the atom number N1 have along with them another hidden variable, which is fluctuations in the initial temperature of the gas also. And those temperature fluctuations are large, and they are also, it turns out, anti-correlated with N1. So if I have a little bit more atoms, then I'll have a fair bit lower temperature. And because of that, evaporative cooling won't evaporate many atoms away, and I'll end up with a final atom number that's very large. And we think that leads sort of as an artifact to this superlinear behavior. In contrast, as evaporation goes on, it turns out it sort of fixes the temperature under almost all conditions. And for these later time data, we think that the initial temperature of the gas is always the same at this point. It's just the initial atom number at, let's say, 150 milliseconds varies from one run of the experiment to the other. And now we're looking more at sort of the native thermodynamic response of evaporative cooling, which we think our data are showing is a sublinear process, which is actually something I would have expected given the dynamics of evaporative cooling. There's another meaning to this super and sublinear process, which is hidden in the question about fluctuations. So now I want to pay attention to...
Dan, can I ask a question?
Yes, you may.
Quite welcome to Pittsburgh, by the way. So,
Yeah, thanks.
Yeah. So does okay, what if you change the density? Would that be more sensitive? I mean, the N2, would they be more sensitive to the density or to the, I mean, definitely it's related to the temperature, but it's not equilibrium, but the density, okay, if you plot versus density, not versus the total particle number you start with, what might happen?
Well, I can't tell you what the density is. What we measure is the atom number.
Mm-hmm.
It's true that if I also knew the temperature, and since I know the size of the trap, I also know the density. Turns out that at lower temperature, the gas would be denser because it would be more concentrated inside the bottom of the trap. But that's, again, going to be kind of a hidden variable for me. At least as we set up the experiment now. What we're measuring is atom number.
Because I was thinking the particle loss and other things are all mostly related to the like interaction or scattering. That would have nothing to do with the, how dilute the system is, the density at
right,
local.
right. Yeah, you're absolutely right. It's a function of a combination of both temperature and number. If the temperature turns out to be kind of fixed, let's say at these lay times, it's just fixed by the effective trap depth, then that's a fixed quantity for all data, and now the variation in n is a proxy for all variations of the system. So then it's a very well controlled problem. But over here at the initial point, there was sort of initial preparation of the sample that was sort of just an artifact that had a little bit more noise than we would have liked.
Can you measure the velocity distribution, maybe by turning off the trap and letting things fall?
Yeah, so that's something I'd like to get to that toward the end, because obviously, well, I don't know. This is really interesting. So I would like to also measure other quantities with the same method, making real-time measurements of other quantities. We've thought about maybe we can expand and shrink the trap as we're making these measurements, and see how much variation there is as the atoms sort of move away from the center of the cavity and back toward the middle. We look at the magnitude of that, and that's an AC measurement, so it's independent of our DC measurement so far. That would tell us something about the size of the gas, not just the number of atoms. And that would be a proxy for measuring temperature. Measuring velocities, maybe that's also in there if we look at the quick time dynamics that we're observing. Maybe there's some kind of signal at, let's say, the trap frequency or something. So anyhow.
Okay,
right,
let's let Dan try to get through his talk so he can get the wonderful things he wants to show us.
It's fine if I get through half of it. This is a lot of fun. Okay, so now I want to pay attention instead to fluctuations, okay, which is, I think, really the more interesting topic. All right, so here's, again, a picture of our non-equilibrium thermodynamic problem. And I think of it as the following. We start off with a total number of atoms, N1, and at some late period of time, the population distributes itself between a fraction of atoms that remains trapped, that's this quantity N2, and then the remaining atoms, this number N1 minus N2, are atoms that have left the trap. And depending on how you want to think about this as a thermodynamics problem, these atoms can be thought of as having just disappeared, or having been transported to a reservoir, maybe that catches them out here, or even still to be confined, but now in a much larger box. Maybe they inhabit some volume outside of the trap. Okay, now we'll ask, why would there be at late times additional fluctuations in the quantity N2? Now there's some fluctuations in the quantity N2 that are just given by the fact that N1 also fluctuates. But let me sort of subtract out those predictable fluctuations and ask you, what's the remaining, I guess, unexplained variance in this quantity N2? Okay, so one source of those fluctuations would be just measurement noise, right? I have a measurement of N2 and it has some noise on it, that's going to lead to variations. I also have fluctuations in the measurement of N1, and I'm using that number N1 to predict the value of N2. So that extrapolates some more noise into my measurement. Okay, so that's the measurement noise. But there's now also physical causes for there to be fluctuations in the quantity N2. So for example, if I just regard that the atoms have been now divided into, partitioned into two categories, one is the atoms that are trapped and one is the atoms that aren't trapped, then maybe the simplest expectation I might have is that there should be noise according to the binomial distribution. There's a certain probability that atoms will have been ejected, and just under coin flips or something, that'll lead a variation in the quantity N2, which is given by this expression, which is the noise of the binomial distribution. But it could be that the physics of evaporative cooling is fancier than that. So for example, maybe atoms don't leave 1 by 1, but they leave 2 by 2 or 3 by 3. So if M is the number of atoms that leave in one step, then that would lead to binomial noise that is larger. So there would be a larger variance in this quantity N2 that shows the loss to be some kind of many-body process. There's also the amplification or damping of number fluctuations, which are basically what I was just telling you about in understanding even the average quantities and how they evolve in time. So if you have evaporative cooling as, let's say, a sublinear process, then fluctuations, let's say binomial distribution fluctuations as they grow, would actually tend to be damped out by the dynamics of the system. So that's going to affect how the fluctuations evolve. We can come up with even fancier ideas for why there would be fluctuations. So one is, let's say I take evaporative cooling and I think about it actually as an equilibrium process. That I have a gas, and then I have the gas now living in a very large box. The evaporated atoms live in this large box out here, but the unevaporated atoms live in this little box over here. I can use equilibrium thermodynamics to describe that situation, and the prediction would be, it also comes out of the grand canonical treatment, that there would be number fluctuations at equilibrium at any point in time for the number of atoms inside of this volume. And those fluctuations are related to the compressibility of the gas. It turns out that if the atoms are non-interacting, they're just bouncing back and forth between these walls, then this compressibility prediction is basically the same as this binomial prediction. It's the Poisson distribution instead of the binomial distribution. But for large N, that's the same. But if the gas is an interacting gas, then I might see changes in the fluctuations in N2. And so my measurement might be telling me something about the compressibility of the gas. Or I can think of this maybe as a transport problem, right? Sort of from, the viewpoint of, let's say, mesoscopic electronics, I can imagine that I have a system where there's some kind of barrier or some kind of current channel. And the system is going to flow current from this area, which is one reservoir, down to this area, which is like another reservoir. And so maybe the flow and the fluctuations in that flow should be treated in some sort of transport formalism. So I think it's an interesting quantity to examine. So here's what we have for that quantity. So this is the unexplained variance in the final atom number. That is the variance that remains after I subtract out the observable correlation with the initial atom number N1. And let me pay attention to this lower graph first, which is where we've looked at these late time data, where we think we're looking at the real natural evolution of evaporative cooling. For different measurement strengths here, I have the dashed line here, which is just the amount of variance that I expect in N2 just from measurement noise. And then I have this solid line here, which is where I add in also the expected noise from the binomial distribution. And then these are the data at various levels of measurement. So what I don't know if I can say anything terribly quantitative about these, but it looks to me like the added fluctuations that I see in the late time data are fairly consistent with binomial noise. At least they're not much higher than expected from binomial noise. So that seems to rule out that we have a situation where atoms are being lost from the trap in clumps of 10 atoms at a time. And it also agrees with this idea that we don't have a strongly superlinear process. In contrast, if I look at the data starting from early times where I do have this strong superlinearity, I have this extra temperature hidden variable that is kind of affecting the dynamics, then you see that also we see enormous fluctuations in how they grow. So this again accords with this observation from the previous slides about the early time dynamics being superlinear and the late time dynamics being linear or sublinear. Okay. With this kind of experimental method, we can also try to not just observe the physics of evaporative cooling, but we should also be able to control it, because we're making real-time measurements and we can respond to that real-time measurement by doing something. And this can have practical use, like it just makes our experiment more robust so that every time we run it, we start with exactly the same conditions. Or if we have our atomic system serving as like a sensor, then that sensor will always, work with the same gain, let's say. So there's real practical reasons for doing so. but I think it would also be interesting from a like an active quantum systems perspective. Anyhow, so here's at least our very first attempt to do this kind of stabilization. So this is using the old method of making atom number measurements. We just have a constant frequency probe. We measure the intensity of light coming out of the cavity, and we just wait until that intensity hits some kind of trigger point. When it hits that trigger point, we stop evaporating, we restore the trap to where it is, and then we come back and measure the number of atoms in the cavity. We want to know whether that number has now been tamed by this feedback method. And the answer is yes. So the initial atom number without any feedback stabilization, is up here. There's large fluctuations in that atom number. And then after stabilization, we come and check the number of atoms in the cavity. Of course, we've evaporated away some atoms so that our feedback has something to measure, and that the final atom number is actually very well controlled by this method. So we're sort of still taking data along these lines, but we're playing around with what is the optimal point at which to operate our sensor. We can certainly stabilize the atom number to a value that's well below the Poisson fluctuations of the atom number, but what the real limits of this method are, we don't totally know yet. Okay, so now I can go on to a second topic, but maybe I shouldn't, because should I be finished by now?
Yeah, I think we're out of time.
We have about 3 minutes, but there were a bunch of questions, so maybe people have some more questions on that topic.
Okay, so I'll kind of so maybe I'll just state that we also have done a sequence of measurements on using the cavity to measure also the spin state of atoms inside of the cavity. And we can measure those spin fluctuations, those spin dynamics very sensitively. So here's a gas of atoms undergoing long-wave precession inside of the cavity, and you see we can measure long-wave precession in real time with very high signal to noise, and start looking at the dynamics and how they're controlled by the influence of the measurement light itself on the precessing atomic spin. So this is an area that I would have told you a bunch about, but I will just skip this part and get to the end. So basically, most of what I told you about is this concept up here. So I think we've hit a pretty rich vein with these measurements. Tom remembers this from when he was in the group as well. You just try something, and you see something in a measurement, and you're like, wow, there's a lot I can do with that. That's real gold. And so I think these real-time measurements of systems undergoing thermodynamics, it seems like there's a lot we can do with it, in particular in this sort of mesoscopic regime, as we start thinking about the effect of interactions, the effect that our gas is a two-dimensional gas, it's a strongly interacting gas, it's right at the verge of being Bose condensed. There's a lot that we can start studying in terms of its thermodynamics, things like heat engines, and then also transport phenomena. So I think we're going to find that there's a lot to study with these measurements. We're interested in developing more types of continuous measurements so we can expand the repertoire of multi-time correlation data that we can obtain. And this has been, for cold atom physics, this has been a long-standing desire, is to make multi-time or two-point or multi-point correlation functions. How do you do that? And I think we've sort of learned how to do that. So I think that there's a pretty big message here for the cold atom community. We're interested, from going on from here, we're interested in studying quantum systems and how they evolve, and also how they're stabilized under feedback. Andrew was talking about simulating quantum matter, but here we would take kind of a different approach. We would, let's say, want to create quantum states that are highly entangled, and instead of building a Hamiltonian and trying to cool a gas under that Hamiltonian, maybe we can construct those quantum states directly using some kind of feedback protocol. So that would be an interesting direction for us to go. Meanwhile, another two big efforts happening in my cavity work. One is we're starting to apply cavity quantum electrodynamics to the problem of photochemistry. So a gas of atoms inside of our cavity can undergo what I would call optically induced chemical reactions, either a reaction from two unbound atoms into a bound molecular dimer, or for example, transition from one bound state to another bound state of a molecule, but induced by light. So that is like photochemistry, like is what is done in physical chemistry experiments. Except here we're going to start examining what the optical cavity does to this photochemistry. And there's a concept that I want to develop, which is where the vacuum fluctuations of the electromagnetic field can direct the chemical reaction toward a specific final state. And then another effort, which is now really highly developed in my lab, is building a new cavity experiment, which is conceptually shown over here, where we'll be able to use optical tweezers to place either ensembles or single atoms at specific locations inside of the cavity, and also use a high numerical aperture microscope to illuminate single atoms selectively inside of the cavity, and start building what Andrew was also implying would be interesting, is a programmable quantum simulator for open quantum systems, where these would be a bunch of quantum elements that are undergoing some interesting quantum dynamics while they are also being observed and perhaps subject to feedback. So that's something we're building, and I can tell you about the status of that, but it's looking really, really great. So with that, let me finish. Here's you know, on a group photo, here's a listing of a lot of the people that were involved in the cavity work. Things that I elected not to talk about today was almost everything, but we have experiments, Vincent knows about these, on atoms and optical lattices, where we're interested in geometric frustration in solids. We have experiments on two-component gases, two different elements, in this case lithium and rubidium, and understanding how magnetization is exchanged between these two gas mixtures. We have some interesting results there as well. I have an experiment that is trying to laser cool things that have never been laser cooled before, and we're starting at this point with atomic titanium. No results to show yet, but I think we have a lot of reason to believe it's going to work. I've been pretty involved in the effort to put quantum gases out in space, where they don't bother anybody, but where microgravity can allow us to study them differently. And then, of course, my life has been turned upside down by the founding of this new NSF Institute at Berkeley, which I'll be directing, and where a lot of great stuff is planned. So I'm really quite looking forward to it. And with that, I'm just going to finally stop. Thanks.
All right, thank you, Dan. There's so much to talk about. 5 other talks on the final slide. Worth of information. Is there like one really fast question from somebody before we unfortunately have to move on? Okay, hearing none. Thank you very much, Dan. Tom, would you be so kind as to load yourself up? Our final speaker is, well, formerly Dan's, but now our own Tom Purdy, who is an assistant professor here at the University of Pittsburgh. Take it away, Tom.
Okay, great. Thanks. I'm Tom Purdy. I'm here at Pitt. So I run a quantum optomechanics lab there. So we've been shut down like everyone else. So it's given us some time to think hard about some actually pretty old topics in measurement and quantum measurement. And I'll tell you about our thoughts and a little bit about how we're making a little experimental progress towards these things. So the topic today I want to talk about is the quantum limits of optical lever detection. So just to put everyone on the same page, so we know what I mean when I say optical lever, you should think about an AFM cantilever that vibrates up and down, and it tilts a little bit as it vibrates. The way that's read out almost universally is you take a laser beam, you bounce it off the back of the cantilever, and you measure the angular deviation of that light by measuring what fraction of light hits one half of a photodetector compared to what fraction of light hits the other half of a photodetector. It's a pretty simple technique, but it's used in industry, it's used in science, it's used everywhere for a very long time for lots of good reasons. It's very robust, it's very simple, and I'll tell you about it's actually quite near quantum limits of noise. So it's actually a very robust technique in terms of quantum measurement as well. So here's just some other examples. People use torsional balances to measure big G, Newton's gravitational constant. Here's an example from a modern experiment at NIST when I was doing research for this talk. Actually, Cavendish's original experiment didn't actually use an optical lever to read out his original experiment, but modern versions do. LIGO down here doesn't actually use an optical lever for their main measurement of gravitational waves. They use a Michelson interferometer, but a lot of the ancillary stuff to get LIGO locked to measure the tilt of mirrors in orthogonal directions, they use lots of optical levers. They know it's a simple and robust technique that works really well. So, to step back, it's really Stone Age technology. People have been using sharp edges and light to measure angles for a very long time. So, sundials and astronomical things. But today I want to focus on the quantum aspects of this technology. So the system that I have is in my lab is a vibrating string. So here's a picture of a vibrating string, and we bounce light off of this string, and we focus our light in such a way that its beam waist is small compared to the wavelength of the excitation of the string, such that basically what we got is a tilting plane that the light is bouncing off of, and we measure it on a split photodetector. So a very simple system. I'll tell you today about how we build our strings a little bit, how far we are to getting to strings that can get to quantum limits of measurement, and also some theory about what these quantum limits are. Some quick facts about optical levers that you may or may not know, and I'll tell you a little bit more about this in the next few minutes. They're within a factor of 2 of an ideal quantum measurement system, and I'll tell you how that works in a few minutes. Their sensitivity is within a factor of a few of what are traditional optical interferometers. That is, taking the same amount of light and the same amount of integration time and just bouncing off of the antinode of one of these vibrating strings and measuring with a Michelson interferometer gives you almost, not quite, but almost the same sensitivity. But they're very robust in that they're insensitive to all sorts of classical noise. There's no frequency discriminating element here. You can use an LED, you can use sunlight. So the requirements in the light are very much less than for interferometers. But even though this is a really old technique, no experimental system has really reached the quantum back action limits, and I'll tell you about what those are in just a few minutes. But first, why would we want to study optical levers? Well, I've done a lot of cavity optomechanics, starting with measuring the motion of cold atoms in a high finesse optical cavity, to measuring the motion of other mechanical resonators in a high finesse optical cavity, to measuring the motion of mechanical resonators in other types of optical cavities. But here, the key, the word I'm using over and over again is cavity, high finesse, high Q optical cavity. And usually, to date, that's what it's taken to really do precise quantum measurements on the state of a mechanical motion, is to have a high finesse optical cavity. People have done things like cool mechanical resonators optically to the ground state, generate squeezed light, entangle all the different quantities involved, entangle 2 optical fields by interacting with a mechanical system, entangle 2 mechanical fields by interacting with an optical system, entangle light and mechanics and any combination you want. People have also devised ways to get around the Heisenberg uncertainty limits of quantum measurement that is called quantum back action evasion. So now in my lab, we're trying to figure out what can we do without a high finesse optical cavity. And if you go over here, we look at sort of the bare minimum requirements to get to an interesting regime of quantum measurement. It's really related to something called an optomechanical cooperativity. I won't go into the details of what a cooperativity is, but it's some measure of the interaction strength compared to how fast energy is dissipated in your system. So the interaction strength is proportional to the optical power and the product of the optical quality factor of your resonator and the mechanical quality factor of your mechanical resonator. So to get to a cooperativity, you can trade off optical and mechanical Q. If we make the biggest trade-off, like a single pass measurement technique, Q is 1. And so here's a set of parameters that I think we can get to in our lab. They don't mean too much to the average person. But the thing to point out here is that we set the optical quality factor to 1, and now we need a mechanical quality factor of 1 billion. So that's the trade-off we're trying to make. And I think it's possible to get to mechanical resonators with a Q of 1 billion, in fact. And that's what the next few slides are telling us how we're going about trying to do that in my lab. So we can get to a Q of 1 billion. We can do all sorts of interesting quantum optomechanics, I think, without the need for a high finesse optical cavity. So how do we build the devices to try and get us to a mechanical Q of 1 billion? Well, we play a few tricks. So you should think about our devices as a long, thin silicon nitride string. So a few millimeters long, but only tens of nanometers thick. So very high aspect ratio. And like any string, the tighter you pull it, like a guitar string, you tune up your guitar string, the tighter you pull it, the higher the frequency. And here, since the aspect ratio is so great from the stress-free string to the tension, we can increase the resonance frequency by 4 or 5, 6 orders of magnitude. So we can really tighten this thing up and increase its frequency. At the same time, the dissipation, the mechanical loss in the string doesn't change very much as I tighten it up. So what's actually happening is this patient's staying the same, the frequency is going up. That means the Q is just the number of oscillations you make before you lose energy, increases by several orders of magnitude in what's referred to in optomechanics as dissipation dilution. So that's one thing we do to make high Q devices. Another thing we do is use acoustic band structure engineering. So if you look carefully at these strings, we actually just modulate the width periodically. And we modulate the width periodically at the mechanical wavelength, such a way that creates an acoustic band structure in our system. And indeed, if we make the right geometry for a unit cell, we can make an acoustic band gap. That is, make some frequencies where acoustic waves can't propagate down this string. In order to make a really high Q optical mode or high Q mechanical mode in the system, what we actually do is introduce a defect in this in this periodic structure along our string, and that makes a localized defect mode. And here's a simulation of a localized defect mode of a modulated string. This has lots of great features. It reduces the loss due to acoustic radiation of the substrate. It does what's called soft clamping, meaning there's no excitation at the ends. And when you have a hard clamp boundary condition on a string, you get a really sharp kink at the edges right where you clamp, and that creates a lot of dissipation. So all these things people have used to great effect to make Q of a billion mechanical resonators. Here's examples that have come out of the nanofab at Pitt, made by my graduate students. Here's a modulated string where one period of the modulation is stretched out to make a defect. And here's again the simulation of what the mode of that defect is supposed to look like. And here's our best efforts to date. We can measure these devices. We measure them at 4 Kelvin. It's about a megahertz mechanical resonator, and we can measure the Q is about 10 to the 8. So that means its ring down time is tens of seconds. Importantly, for talk about quantum optomechanics here, if I put this mechanical resonator in the ground state via some sort of cooling, it would actually stay in the ground state for about 1,000 oscillation periods before even 1 photon's worth of thermal energy would hop onto the system. So we're already able to build something that's got some quantum aspects for at least a short time. And we think by improving the geometry, increasing the stress, making cleaner materials and things like that, we think we can get to Qs of billions and 10 billions, at least at these low temperatures where we like to do our experiments. Indeed, most of quantum optomechanics is really just fighting thermal noise to get to the interesting quantum stuff that's usually hidden underneath for most mechanical systems. Okay, so that's a little bit about what we built in our lab. We're still building that up and testing that. We're getting back online to make new and better devices. So I thought I'd switch gears to talk a little bit about the theory of quantum metrology here. So quantum metrology has a quantity called the quantum Fisher information. And for those of you not familiar with the quantum Fisher information, it's just a way to tell, given some measurement, how much information can you extract from that measurement. That's what the quantum Fisher information says. It's how much measurement, how much information can you extract in principle from any given measurement. That leads to what's called a quantum Cramer-Rao bound. For this case, if I know how much light and in what spatial configuration I'm bouncing off my mechanical resonator, it'll tell me what's the minimum uncertainty that I could get if I correctly analyze that light in the angle of rotation of my mechanical elements. And so you can then calculate what the signal to noise or what the information you get from just using a simple split photodetector is. And it turns out it's about 0.64 times the absolute maximum information that you could get. So another way to say this, I like to say that a split photodetection, this optical lever split photodetection is 64% quantum efficient. Another way to say that is that what we've done is just said, each photon, does it land in the left half of the detector, or does it land on the right half of the detector? If we more carefully took into account the exact location of each photon, we would only get a little bit more information. We're already getting 64% of all the information there is just with a 2-pixel detector effectively. So that's good news. Optical lever is simple, robust, and not so terribly quantum inefficient. So I've always felt that quantum Fisher information is a little abstract. I think a slightly better way to explain this is in terms of a simpler Heisenberg uncertainty relation. And so that's what I have in this slide. I don't have too much time to go into detail, but a Heisenberg measurement disturbance uncertainty relation tells us that if I want to make a measurement, there has to be back action in my system. In other words, if I'm measuring position, there has to be a momentum kick to the thing I'm measuring. and my uncertainty, my displacement times the uncertainty of the minimum kick is larger than h bar over 2. That's your classical Heisenberg uncertainty relation. And another way to say that is that if I don't put back action on my measurement, then I can't make a measurement. Or another way to say that is that if I calculate how much back action, in this case, how much force noise from a bunch of random photons recoiling off of different parts of my mechanical resonator, that's what causes back action in the system. If I calculate how big that force noise is, that puts a strong bound on how much information I can extract. That's equivalent to the quantum Fisher information in this situation. So what we do here is calculate these quantities for our optical lever detector. So what I have on the vertical axis of this graph here is just the noise for my measurement. And what I have on the horizontal axis here is basically how big my laser spot is compared to my mechanical wavelength. So over here in what I call the optical lever limit, I've got a tightly focused laser that's sampling only a linear part of the sine wave of my mechanical mode. Over here in what I call the diffraction grating limit, I have a large Gaussian beam that interacts with many periods of my mechanical resonator. Effectively, I'm bouncing off a sinusoidal diffraction grating. And it's not so surprising here that in the optical lever limits, my system looks like an optical lever. I get information out based on looking at it with a split photodetector. But over here, you think about what happens when I bounce light off a diffraction grating. It doesn't just tilt its angular deviation. I get 2 first-order diffraction spots. And those 2 first-order diffraction spots are quite symmetric if I come in at normal incidence for a sinusoidal diffraction grating. So counting the amount of photons in the left half versus the right half of my photodetector doesn't give me any information about my mechanical motion. It's not to say there's no information in that beam. It's just to say that using a split photodetector is a terrible way to make that measurement under those circumstances. I want to measure something else, some other quantity of the laser to get more information out. And that's really summed up in these graph here. What I got here in this blue curve is the noise floor of a measurement. So this is the shot noise limited noise floor of my measurement, and it's normalized to units where 1 is a perfect ideal quantum measurement. And as I make my beam, my laser spot bigger and bigger, I actually get a lower and lower noise floor. That's because now my laser is sampling a larger and larger amplitude of motion region of my mechanical resonator. So my sensitivity goes up for a while. At the same time, my back action goes up. That's because more and more photons can bounce off of parts of the mechanical resonator that are able to move more easily or have a bigger lever arm, so I can provide a larger optical torque to my rotating object. So again, the back action doesn't go away in this diffraction grating limit, but my signal noise gets much worse. So we can take the product of these two things and calculate this Heisenberg measurement disturbance product, and we can see that, or I can take red as this Heisenberg measurement disturbance uncertainty product, yellow is just 1 over that. It's equivalent to a quantum efficiency, and you can see I can make a quantum efficient measurement in this diffraction grating limit. Over here, I'm making a terrible measurement because I'm not measuring the right quantity, but there's still a lot of back action. So that's the very basics of quantum measurements in this type of setup. And now we can ask ourselves, how can we avoid the effects of quantum measurement back action? That is the fact that photons are bouncing off of my mechanical resonator, causing forces and torques, making it vibrate. That's causing my light to reflect at different angles and making extra noise on my photodetector. How do I get rid of that? And that's most easily described with this ray tracing diagrams. So over here, I just have a laser, and it's got some Gaussian spot coming out of it. So many photons go through, are in the center of the beam, and there's also some photons out on the wing of the beam. And those photons bounce off of some tilting lever and hit my photodetector. Now, if my lever tilts a little bit, that's a signal I want to measure. Of course, just the angular reflection changes and I get more photons on one side of my detector than the other. That's just regular old optical lever detection. But now I ask myself, what if, what's different about the motion or the signal driven by optical forces or optical back action? Well, you ask yourself, a ray that goes right through the center here and hits the pivot point of this lever, it doesn't cause any motion because there's no lever arm, there's no torque if I put a force right at a pivot point. So that light just goes straight through my system, hits the photodetector exactly where it would, independent of anything else. But this photon, which is off on the wing of the Gaussian, has a larger lever arm. It can actually tilt my mechanical object, and that causes the angle of reflection to tilt a little bit, and that causes a little bit of angular deviation in the output beam. One way to think about it is effectively what we've done is we made an optical force induced diverging lens. That's the effect of optical back action in the system. And well, how can I counteract the effects of a diverging lens? There's actually a really, really simple way to do that. I add a converging lens to my system, and that's actually all it takes to be able to erase the effects of back action on my optical lever detection signal. So here, if I just trace rays through now my system with a lens, you can see the ray that was tilted due to back action goes through my system a little differently than the ray that wasn't tilted. And to reduce the back action, all I got to do is move my detector down to this point where I'm no longer sensitive to those tilts induced by back action, and I can reduce the quantum noise in my measurement. So probably out of time, but there's certainly another way to describe this in terms of what I can do is take my laser and expand it out in terms of Hermite-Gauss polynomial beams, and when I send those through a lens, those all get different phase shifts, different GUI phase shifts it's called. When I have different order Hermite-Gauss polynomials in optics going through a lens system, they each get different phase shifts along the beam path, and I can interfere different phase of different optical modes, and that creates the same effect. Is sort of the physical optics description of what's going on here. And so we hope to do this in my lab. Stay tuned. Maybe next year we'll have the actual real data about how this works, how we can avoid the effects of back action and make interesting quantum measurements just by taking a very simple system and adding yet one more simple optical element, a simple lens. With that, I'd just like to conclude and thank all the students in my lab who are working hard on this and other projects. We're working on a bunch of different projects. The one that's caught my attention today is this quantum limits of optical levers. I'd like to thank everybody, and if there are any questions now, I'd take those.
We're clapping on the inside, Tom. Sorry. So can I ask, if you were to go back the one slide, so it sounds like you would also do better maybe if you used a camera with more pixels here, if you didn't have the mirror?
Yeah, so in principle, if you use a camera with fine pixels, you can get from Fisher information 64% up to 100%. And there's a really simple algorithm. All you do is find the center of mass of your Gaussian if you have a shot noise limited resolution on each pixel of your camera. The problem with that for us technically is we have high frequency mechanical modes, and cameras typically aren't fast enough to capture the changes at the mechanical frequencies we care about.
But then does the lens sort of sets it up so that, you know, having that advantage doesn't help at all. So that's kind of it represents an erasure of unwanted information.
Yeah, so the lens is erasing unwanted information, indeed.
And that's why it's squeezing, I guess, because usually when you can sort of take some information you don't like and tuck it away where it's not accessible, that's usually some squeezing effect.
Yeah.
Dan doesn't like this.
There's a lot of ways to describe this. You know, more formally, you can say what's happening here is that you're scattering, whenever I tilt the beam, I'm scattering photons from my 0th order Hermite-Gauss polynomial to my 1st order Hermite-Gauss polynomial. And there's actually correlations between amplitude and phase in that 1st order Hermite-Gauss polynomial mode. And those correlations lead to a squeezed 1st order Hermite-Gauss polynomial mode. And in order to detect a different quadrature of that, to detect along the minimum quadrature of squeeze, as opposed to the anti-squeeze quadrature, I have to interfere with a certain phase local oscillator. And the lens is what allows me to do that, because that changes the phase of the 0th order Hermite-Gauss polynomial relative to the 1st order Hermite-Gauss polynomial. They interfere on my detector, and I can map out different quadratures of this correlated 0-1 mode by moving my detector along the beam path. Is a more formal description.
Okay. Other questions?
Yes. So actually, yeah, Michael had asked my initial question, but I have a follow-up question on that, which is, I mean, I understand that like using like some kind of CMOS camera is not compatible with the speed and everything, but it's not clear to me that you need to go to like 1,000 pixels. And I guess what I was wondering was, how does this Fisher, whatever the efficiency, quantum efficiency approach as a function of the number of pixels that you have? Because I'm sure you could buy something with like 3 or 5 pixels, and maybe you get up to like 95%.
Yeah, so we are we're working on that. I have a student who's building a 16 pixel array to do basically, if you build a 16 pixel photodiode array, you can weight each pixel correctly in post-processing. So you can weight the photocurrents of each pixel according to a certain weight and come out with the optimal signal to noise. And I think even with just 3 or 4 pixels, you can go from 64 to 80% efficiency. So it scales pretty quickly.
Suppose suppose your power is limited so that you can't just raise the power to increase that cooperativity. Like, let's say you're down to the single photon limit. I might have some oscillator or something that's strongly affected by the light in other ways. You know, I don't know, heats up. I'm thinking of my own systems, which sometimes respond like that. I'm just wondering if would this approach, can we use it to like somehow increase the information I get from that single photon or a few photons?
This doesn't necessarily, this allows you to get, to remove the unwanted noise from back action. It doesn't increase the sensitivity otherwise. In fact, you're actually decreasing the sensitivity. So the idea with this back action evasion scheme, you are reducing both your signal and your noise, but your noise is reduced more than your signal is.
I see.
So your net signal noise goes up.
Okay, thanks.
Okay. Well, I think we're not egregiously over time. And so it falls to me to thank everybody for attending today. Thank you to our speakers and to the invisible internet audience. So let's unmute and clap audibly this time for all our speakers today. Yeah. All right. Thank you very much.
Yeah. Thanks.